Assalamualaikum and good morning. My name is Ahmad Fuzami and today I would like to present about my research topic which is electrochemical evaluation of nickel oxide addition towards lanthanum, strontium, cobalt, ferrite, cathode for intermediate temperature solid oxide fuel cell. My slide consists of three parts, namely introduction, methodology, and result discussion plus conclusion. What is fuel cell? Fuel cell is a device that converts chemical energy into electrical energy. But in solid oxide fuel cell, the conversion produces a clean waste. Therefore, it was categorized as a clean energy. The process involved in SOFC is oxygen reduction reaction process. The component consists of cathode, electrolyte, and anode, and require oxygen and hydrogen to act as a fuel and produce water as a result. In this presentation, I focus on the cathode side, which mainly target to improve the oxygen reduction reaction process. With the current challenging listed as above, it is desired to have lower operating temperature while sustaining the cathode performance. Thus, my solution is implementation of LSF-NiO composite cathode. In order to further discuss the problem statement, I would like to focus on the reaction that occurred in the cathode side. As showing in the figure, the process involved in the cathode side limited only at the triple boundary phase between cathode and electrolyte. Thus, they require higher operating temperature for more ion transfer to be happen. In depth onto the situation, current cathodes such as LFCF need to be operated at 1000 degrees Celsius to yield enough energy for the power plant. But continuously conducted at high operating temperature, the cathode tends to react with chromium which came from the reactor itself, and this called as a degradation of the cathode. One way to avoid this is to reduce the operating temperature so the chromium won't react with the cathode, and this will allow the cathode to sustain its performance. The right side shows the oxygen reduction reaction take place beyond the cathode surface. Thus, why nickel oxide as the candidate? As reported in the several articles, I believe the addition of nickel oxide capable to improve the oxygen reduction reaction rate due to the high conductive material, good carbon dioxide resistance, and capability to act as a sintering aid. Now we move on to the research objective. As listed, I would like to synthesize the LSF NIO via enhanced modified Sol-Gel method. After conducting a pre-characterization, optimization process will take place and this will be done via electrochemical analysis. Next, comparison between LSF NIO and bare LSCF will be done in terms of electrochemical performance, and lastly, a single cell application will be conducted to prove the capability of LSF NIO operated at intermediate temperature range. Next, we move on to the methodology. The LSAF powder was synthesized via enhanced modified Sol-Gel method via following details. The pH of the solution was controlled using ammonia solution at 7. There are noticeable color change between pH 1 to pH 7 as depicted in this figure. Next, the solution was heated at 100 degrees Celsius to form a gel. The resulted gel then calcined at 800 degrees Celsius for 6 hours to form the LSCF powder. To produce a composite cathode, 95% of LSCF powder was mixed with 5% of nickel oxide. The powder mixture was milled together with ethanol for 2 hours and it was sintered at 800 degrees Celsius for 6 hours. The resulted LSCF NiO powder then will be sent for characterization and the symmetric cell processing. The symmetric and the single cell processing will be done via screen printing and the result was shown in the figure C. Next, we move on to the result discussion. First is the pre-characterization. In pre-characterization, I would like to summarize that my finding as LSF NiO was successfully being synthesized via enhanced modified Sol-Gel method at 800 degrees Celsius. Thermal analysis suggests that the LSF perovskite start to form above 570 degrees Celsius and bonding analysis further confirm trace of carbonate bond almost disappear at 800 degrees Celsius. Calcining LSF NiO at 800 degrees Celsius, phase analysis confirmed that the LSF NiO formation as no tertiary phase occurred in the sample. Next, we move on to the optimization analysis. The optimization part in this slide revealed that the optimum NIO addition found to be at 5 weight percent of all NIO loading content. According to the literature, possible explanation occurred on the increasing of ASR for 7 weight percent of NIO and beyond, subjected to the excess NIO particle that block the LSF pores. Previously, LSCF with 5 weight percent of NIO was chosen as the optimal ratio for the LSCF NIO cathode. This slide compared the LSF NIO with bare LSCF, and it revealed that the major improvement occurred at low frequency impedance P1 subjected to the oxygen reduction process occurred in the cathode site. Thus, it was proof that the addition of NIO indeed improved the oxygen reduction process as claimed in the problem statement before. Lastly, a single cell of LSF NIO and bare LSCF was compared to each other at the operating temperature 650 and 600 degrees Celsius. Both shows capability to operate at lower temperature, and the addition of NIO indeed improved the power density by 25.35%. The activation energy graph also supported this finding, where the activation energy for the LSF NIO found to be much smaller than the bare LSCF. As a conclusion, previously it was confirmed that the LSF NIO was successfully be synthesized at 800 degrees Celsius, which answered the first objective. The optimization process from the electrochemical and the BET analysis suggests that the 5 weight percent of NIO is a sensible addition amount for the LSF NIO cathode, which summarized the second objective. The third objective was answered by the boat plot that revealed that the low frequency impedance of the LSF NIO far smaller than the bare LSCF. Finally, a single cell of LSF NIO capable to improve the power density by 25.25, which finalized the fourth objective. That's all for me. Thank you.